Welcome to You Got Hope Chemistry. I'm Hope, and you're about to learn some chemistry. In today's lesson, we're going to look at 3 additional types of stresses. However, 2 of the stresses we are going to look at actually follow under a addition removal scenario. I just take them out as their own stress because I find that students really struggle with the concept of what would happen in a Le Chatelier's principle question if there was a neutralization or if there was a precipitation. Now, the other one we're going to look at is the addition of a catalyst or an inert gas. Now, I want to clarify, this really isn't a stress. It doesn't actually cause any kind of shift, but you do have to understand what is going on at a very, very basic level. So we're going to start with that. We're going to look at adding a catalyst or an inert gas and talk about what's going to happen. So starting with number 4, which is adding an inert gas and catalyst, we're going to talk about an inert gas. Inert means it won't react. Now, based on simple chemistry and what we've learned about the periodic table, we know that noble gases, other than xenon, are really an inert gas. So we're looking at things like helium or argon or neon most commonly. Now, there's a couple of different scenarios. You could have an inert gas at a constant volume. So what that would mean would be I'd have to have a rigid reaction vessel, like a big steel vessel that cannot expand or contract. It doesn't have a piston, so it has a constant volume. Let's just make up a number. Let's say it's like 1 liter. When you add an inert gas to that, it's not changing the volume of the container, which means the concentrations are unchanging. Now, in order to cause a shift, you would have to change the concentration or the volume of something or the temperature to cause a shift. So this essentially has no effect on the equilibrium other than it increases the total pressure within the system. But because we are not doing Kp, we're doing Kc, which stands for equilibrium concentrations, and because none of the concentrations are actually changing, we've just added more stuff, different stuff to the system that's not part of the reaction. There is no shift. And graphically, you couldn't tell. So let's say I had 2 substances, A and B. The lines were flat, and they said at time X, there was a something was added. But the lines keep going flat. Then what that tells you is, okay, this is either an inert gas because it hasn't caused a shift in any way. A shift is going to cause the lines to go up vertically, up or down, or it's going to cause them to gradually move up or down, but those lines are going to change in some way. The fact that they have not changed in any way is telling me really I've added an inert gas or I've added a catalyst to the system. Now, there is another scenario, which is you could have an inert gas added to a system which volume could change, so something like a piston. Now, that's going to cause the change in concentrations, and it's going to cause the graph to look different, but that's beyond the scope of where we are in chemistry, and you don't need to know it. So at this point, all you really need to know is when you add an inert gas, there will be no shifting taking place. There will be no changes in concentration, and a graph will essentially look identical to what it would look like if it was not added. Now, using a catalyst, we need to understand what that would do. Now, adding a catalyst will speed up the forward reaction, and it will speed up the reverse reaction. Equal amounts. Now, if you're speeding up forward by 5 times and reverse by 5 times, then you're still at equilibrium, and there's not going to be a net difference in the concentrations of products and reactants because we're getting equal speeding up. Right? At equilibrium, the forward and reverse reaction are going at the same rate. So if we're speeding up forward and reverse at the same rate, we're still at equilibrium. Now, if you're wondering why bother doing this? Sometimes you need a catalyst to get a reaction to happen within a meaningful time frame. So this gets the system to equilibrium faster. Okay, we have chemical reactions that happen in our bodies that if we never had a biological catalyst to carry out the reaction, it would take thousands of years for the reaction to happen and we just wouldn't exist. Catalysts are extremely important to get a lot of chemical reactions to even happen. Now, tying this into thermochemistry, remember a catalyst will not change an enthalpy value. It just decreases the amount of energy required to get the reaction to happen, which is called activation energy. And in equilibrium, it speeds up the forward and reverse reactions by an equal amount, therefore getting to equilibrium faster. The graph would look the same. It would be flat lines, and you wouldn't know something happened unless the question indicated that something was added at a certain time frame. So that's the first of our 3 things we're going to look at. The next one is neutralization. Now, really what's happening in a neutralization question is something is being removed, but it seems really weird because you're actually adding something into the system in order to remove something. So I often call neutralization and precipitation removal by addition. Removal by addition. So let's look at the stress, and we're going to look at the chemical reaction, and we're going to notice how bizarre this seems. So the stress says we're going to add hydrochloric acid into the equilibrium mixture. So the normal thing to do would be just to look at the chemical reaction and look for HCl, and then I would increase that concentration and it would cause a shift. But this is not HCl. This is not HCl. This is not HCl. And I don't care about the water because it's liquid. It's not part of the homogeneous mixture of aqueous, aqueous, aqueous. All right. So the next thing you would do is you would create a species list. So the species list for this is H plus or H3O plus and Cl minus. We really treat these as being the same thing. They're acid. Now, because this is a strong acid, it ionizes 100% and it splits into those ions. So now I go back up to the list and I look and I say, well, do I have H plus or hydronium? No. That's a weak acid. It stays as a molecule the majority of the time. This is not. This is not. That's weird. I don't have this or this in the equation. How about Cl minus? I go back. Maybe I have Cl minus I'm adding in. No, no, no. Oh boy. This seems really confusing. When you get to this point, what you need to do is you need to think of one of 2 things. This is either a neutralization or this is going to be a precipitation. Essentially, when you get to the point and you have no clue what's going on, these are probably your answers, or one of the 2 is going to be your answer. So what I'm going to do is I'm going to first look at neutralization. In order to have a neutralization, you need to have an acid react with a base. Now, a base generally has hydroxide in it. Now, there are bases that don't have hydroxide as well, but a strong base will have hydroxide, and an acid will be either H plus or H3O plus. So when I go back up here and I look for a base, because I know I have acid, this is an acid, I go across and I go, oh, this is a strong base. Sodium hydroxide is a strong base because it's Na plus and OH minus. So what's going to happen is this. There's going to be a neutralization reaction. So the H plus or H3O plus from HCl is going to react with the hydroxide ion and sodium hydroxide. So this is a shorthand for HCl. This is the shorthand for NaOH because those are the actual species that are going to react. And this is going to produce water. Now, I don't care about the water because it's liquid, but I do care about this hydroxide. This hydroxide is being consumed. It's being used up. It's being neutralized. I'm removing the OH minus by the addition of hydrogen ions. By adding in hydrogen ions, they neutralize the hydroxide. That causes the concentration of hydroxide to go down because it's becoming part of water. So using our arrows, what's happening is the following. The sodium hydroxide concentration is being removed by neutralization. This is causing then a shift towards the reactants to make more sodium hydroxide to get back to our equilibrium constant. In doing so, the concentration of sodium hydroxide is gradually going to increase, and so is the H2S. And of course, the product concentration must decrease. Whichever side I shift towards, my concentrations increase a bit. Whatever side I shift away from, those concentrations are going to go down. So I call it removal by addition. I removed sodium hydroxide through the addition of hydrogen ions. In our next question, we're going to look at a precipitation reaction, which is another type of removal by addition. So it's going to have a similar feel in terms of we're going to look for the substance being added in the main equation and it's not anywhere, and it causes a lot of confusion. Now before we talk about that though, I would like to talk about the state, which you probably have rarely seen, if ever at all. Al means dissolved in alcohol. AQ means dissolved in water. Now, another way of saying dissolved in alcohol is to give the specific type of alcohol. So I've also seen this reaction, which is a really famous equilibrium reaction, written with the state ET, which essentially means dissolved in alcohol, but more specifically ethanol. So because this is a homogeneous mixture, I wouldn't cancel out water. So normally if water is a liquid and everything else is aqueous, I would cancel out the water. But the fact that this is alcohol and everything else in here is alcohol, this is a homogeneous mixture, and I wouldn't cross out any of the species. They are all going to impact shifts, etc. So for instance, hypothetically, if I added water to the system, this would increase and I would shift this direction. Okay, little off topic, but we'll get back to it right now. So let's say we had this system. It has two ions that have distinct colors. This is a cobalt complex ion, which is pink in color, and this is a cobalt complex ion, which is blue in color. If the mixture together is about roughly the same concentrations of these and these, you get a nice purple color to start. If you get a shift towards a side which has a color, you will cause that equilibrium mixture to look more like that color. So for instance, if I add chloride ions, it would cause a shift to the right. It would make what is blue and it would consume what is pink, causing the solution to look more blue than pink. Conversely, if I added water, that would cause a shift to the left. That would produce more pink, and it would consume more blue, and the solution would turn pink. This is a very common question. So the question may say something like this. When a solution of sodium chloride is added to the solution, what color will the system turn? Sodium chloride increases. I shift towards the blue side. The solution would become more blue. Let's look at our stress. It will cause a shift, which will cause a color change. So the stress itself is adding silver nitrate. So the first thing you do is you just look for silver nitrate in the balance reaction. No silver nitrate, no silver nitrate, no silver nitrate, no silver nitrate. The next thing you would do is make a species list, because maybe we're looking for just one of these two ions. So we got Ag plus and NO3 minus. Now anything with nitrate is 100% soluble, so we have to assume it's going to dissolve. I look for silver ions in the chemical reaction. No silver ion, no silver ion, no silver ion, no silver ion. I don't know what I'm doing. I look for nitrate. No nitrate, no nitrate, no nitrate, no nitrate. Well, I'm really confused. When I'm really confused, you should ask yourself this. This is probably going to be either neutralization, or this is going to be a precipitation. So let's look at AgNO3. Is this an acid or a base? No. Are anything up here, based on the knowledge we currently have, acidic or basic? Currently, based on our knowledge, none of that stuff is acid or base. So this can't be a neutralization. So I'm left with the idea of precipitation. So let's ask ourselves, is nitrate soluble with anything or insoluble with anything? And the answer is no. This is 100% soluble with everything. I'm going to remove this from the idea that it's part of a precipitation because it cannot precipitate anything out. On the other hand, silver is very, very insoluble with many, many ions. Now, of course, it would only be insoluble with something which is a negative ion, an anion, to form a precipitate. So that would rule out it forming a precipitate with this compound here. And it would rule out water because water isn't charged. The only two possibilities that it could precipitate out would be the chloride ion or this cobalt chloride complex. Now, looking at a basic solubility table underneath chloride, you will notice that silver is insoluble with chloride. So the reaction that would take place for sure would be Ag plus, in this case, Al, because we're not dissolved in water, plus Cl minus Al, and this would turn into AgCl solid. This would be our precipitate. Now, I cannot look up this cobalt chloride complex in the solubility table. So I'm just going to have to make the assumption that we're removing the chloride ions through precipitation. So let's do our arrows. As chloride is removed when the precipitate is being made, the system wants to bring up the concentration of chloride. In order to do that, it would have to shift towards the chloride side. In doing so, the amount of chloride would increase, and so would the concentration of this cobalt water complex, which is pink. And then the concentration of this blue cobalt chloride complex would have to decrease. So I'm using up what is blue, and I'm creating what is pink. So the equilibrium mixture will turn pink. In this last section, we are going to look at another color change equilibrium system. It has two different colors. So the dichromate is orange in color, and the chromate is yellow in color. And so it's a little bit in between when you have about equal concentrations. And so you can cause a shift to the left to turn it orange or to the right to turn it yellow. The next thing I would do is actually highlight the states and cross out anything that is not part of the homogeneous mixture. So that would include water. I really don't want to focus on that. Now, in the review of stresses, it says the addition of barium nitrate, and then it says barium is insoluble with chromate. This should have a 2. But it's not on our solubility table. So I have to assume that this is the truth and that this reaction is happening. Ba2 plus aqueous would react with CrO4 2- aqueous to form the precipitate BaCrO4 solid. So essentially what has happened is I've removed the chromate ion through the addition of barium ion. So this is going to cause this to go down. Now, if the product concentration goes down, the system wants to shift towards that side to bring that ion concentration back up. That causes this concentration to go down, and this concentration to go up, and this concentration to go up. So we would end up having it turn more yellow because it's shifting towards the yellow side. And actually, a byproduct of this also would be that the pH would decrease because I'm creating hydrogen ion, which is acid. Now let's look at two other scenarios. What could we do to shift the reaction to the left? What color would the equilibrium turn? And how could we shift the reaction to the right? And what color would the equilibrium turn? Now, if I'm shifting to the left, I'm pointing towards what is orange. So no matter what, as long as we are shifting to the left, we're going to look orange. And if we shift towards the right, which is this direction, we're shifting towards whatever is yellow. And so the solution is going to turn yellow. I'll go over that so you can see it better. Okay, now in order to get it to shift to the left, there's a number of things I could do. I could remove the Cr2O7 2-. That would cause a shift to the left, turning it orange. Now, I don't know off the top of my head any ions that just remove Cr2O7 2- and not CrO4 2-, but theoretically we could do that. 2, we could add chromate, CrO4 2-. If I add a product, it's going to shift towards the reactants. So I could add a solution, let's say, for example, I could add solid sodium chromate to the solution. It would dissolve, the chromate goes up and it shifts to the left. Or 3, I could add H+. For example, I could add any of the strong acids, HCl or HNO3. That would turn into H+, which would then increase the concentration of the products and shift towards the left. We've already done one way of shifting to the right, which was to, 1, remove the CrO4 2-. For example, I could add barium ion, okay, or barium nitrate, and that would cause a precipitation and it would shift towards the right. 2, I could remove the H plus by adding strong base. That would be a neutralization. So what would happen is the H plus would react with the OH minus. This would form water. That would decrease the concentration of H, causing a shift to the right. Lastly, I could add reactant. So I could add Cr2O7 minus. Example, potassium dichromate, which is 100% soluble, could be used. And that would cause the reactants to go up, which causes a shift to the right. I hope you have enjoyed this lesson of You Got Hope Chemistry. See you next time.